Right, so while waiting more students to come in, let me just go through a recap of the stuff that we have gone through last lesson. So actually, the main concept that we've gone through during our Wednesday lesson is the intermediate value theorem. And this IVT makes use of the continuity condition and states that if you have a continuous function between a closed interval a to b, then if your function is continuous, then it is intuitively clear that your function value, right, must pass through every single value from f of a to f to b to f of b. All right. So which means, right, if you have some input x value input c, right, that resides between a to b, that implies that f of c, this function value, must be situated in between f and b, right? So you can see this one-liner definition of the IVT there. And I keep mentioning that the important condition in order for you to use your IVT, right, is actually the continuity condition. Okay, so clearly we also gone through an example whereby if your function is not continuous, as you can see, there's an asymptote here, right? And therefore there's a discontinuity at x equals to 0 for this function 1 over x. Then clearly you cannot apply the IVT, right? Because we have no value of c that will give f of 0 is equal to 0, right? Even though we are clear that one side of the function gives negative, the other side of the function gives positive, okay? So because of the discontinuity, right, the function value will not or might not pass through y equals to 0 or f equals to 0, all right? So continuity is important. So the usefulness of the IVT actually, one of its practical applications is in the bisection method. Okay, so the bisection method allows us to find the root of a function. All right, and in fact, this bisection method is very powerful. The reason is because it will be able to handle any function, right? It will be able to handle any function as long as it is continuous within the interval in which you want to find the root for. Okay, so we have gone through this manual example of how we can calculate the root, right, or the approximation to the root using a manual calculation, right? You keep on bisecting or you keep on calculating the function value at the midpoint, right? So of course, this is most easily achieved by a program, or you can also use a spreadsheet software to do it for you. Okay, so certainly in your upcoming midterm exam, you'll be tested on the IVT. So therefore, you are expected to do the calculation. But however, if you can use a spreadsheet software to check your results, you may go ahead and do so. Okay, so predominantly, I want you to apply this bisection method or apply mathematical methods through your computing, okay, through your computer. So therefore, I can allow you in the upcoming midterm exam, you can write a program. You can also use a spreadsheet to perform the bisection method. But however, because your exam is actually right on a piece of paper, so therefore you will still need me the working. Okay, so you can show me the working, but you can use your program or spreadsheet to check your answer. All right, so I suppose that is good for you as well. Okay, so therefore you can observe that in this example, we're supposed to find the root of this function 1 minus x squared minus sine x. So clearly there's no analytical solution for this, right? Because there's an x squared here and a sine x here, so it's not possible to factorize out x, right? And then use some root formula, for example. So hence, we are going to use this numerical method known as the bisection method. But before we do that, we apply the IVT to search for the interval, right, where the root resides, okay, where at least one root resides. So therefore, we found out that there is a transition, right, of the function value from negative to positive over minus pi to 0. As you see here, it passes through the x-axis, so therefore giving us a root there. And then subsequently, it changes the sign again from positive to negative, and hence we discovered another possible root within that interval 0 to pi. So you can see that there is at least one root in each of these two intervals, and then we perform the finding of the root in minus pi to 0, okay, using this simple Python code here. So of course, maybe you can take some time, right, and try to find the root or find the other root in the other interval, okay, in 0 pi. Okay, so this one I'll leave you to try out on your own. I'm not sure if you guys are using Python, right? But it doesn't matter which programming language you use. You can use C or whatever, right? So therefore, the syntax of the code is as such. Okay. So today we are going to, and we also covered, I think, the first example of defining derivatives. Okay, so basically, derivatives are also called differentials. And basically, if your function is f of x, then basically the derivative of the function, right, is actually df dx. Okay, or sometimes we write y equivalent to f of x, right? Then df dx is also commonly written as dy dx. Okay, and then the shorthand notation is actually y prime. Okay, personally, I prefer this notation because it's a lot easier to write. So prime, right, it just means differentiate once. Okay, prime, differentiate twice, and so on and so forth. Okay, we'll come to this more in a while. So then we talked about the tangent problem. Not exactly a problem, but it's just how we can define the gradient of a tangent precisely, okay, using mathematical so-called expressions. And then we look at the concept of a secant line, right? So you can see this is a secant line. So it's just a fancy term, right, for saying that you can have a line connecting between 2 points on your graph. Okay, on your curve, right, you can have a line connecting between 2 points, and that is known as the secant line. And then we say that, well, if you take the limit that make h, right, go to 0, so which means make point 2 go towards point 1, right, then clearly you will see that the tangent line will appear. Okay, if you can go infinitesimally close to point 1, or rather let h approach 0, then definitely you are going to obtain the tangent line. Okay, so the tangent line, as we have discussed, right, as well as visually, it also looks like it is indeed the best representation of the slope to the curve at a particular point. Okay, so we also call that the instantaneous rate of change of that curve. Okay, of the curve at that point. So I mentioned before that this is indeed the first principles definition of differentiation. Okay. In fact, some of you may have gone through differentiation or calculus in general in your secondary school, right, as well as your poly days. You might not know this because usually what the teacher will tell you is that you have a table of differentials, right? For example, differentiate x to the power of n, you will bring down the n, then after that the power becomes n minus 1, right? And then if you differentiate, for example, sine x, you get cosine x, differentiate ex, you get ex, so on and so forth. So therefore, you have a table of differentials, right? But however, in this university education, right, we want you to understand how these guys comes about. So therefore, we are going to derive some of the identities of differentiation that you have learned previously. Okay, so we're going to look at why is it that when you differentiate, for example, sine x, you get cosine x. Why is it that you differentiate 1 over x, you get minus 1 over x squared, right? Everything can be derived from this first principles definition of differentiation. I think we've gone through one of these examples, and the function here given to us is f equals to x squared. So it's supposed to find the slope, right? So typically, we will find the general expression for f prime first, okay, or the gradient. So in this case, this gradient here, right, is also equivalent to f prime. So this guy is actually also equivalent to the f dx, or dy dx if you want to call it. So df dx, which is equivalent also to f prime x. Okay, so this f prime x is actually equivalent to 2x. So I think most of you would have learned that differentiate x squared, right? You just bring down the power 2 minus 1. So hence, you clearly will get your 2x. Okay, so we all know that this definition is definitely correct, or this process, right, is definitely correct. Okay, agree with what we have learned previously. And by the graphical inspection, you can also see that this is indeed making sense. Okay, so when x is equivalent to minus 2, and this guy is a 4, because minus 2 square gives you 4. So you can see that we get a negative 4 as our gradient by substituting minus 2 into x. So therefore, this looks logical, because the negative gradient, right, agrees with the downward slope, okay, that you get over this interval, okay, over the negative x interval. So today we're going to move on to finding more differentiations or finding more derivatives, right, using the first principles definition. And also later on we'll look at the concept of rate of change, mainly pertaining to the input or the independent variable being the time variable. So, okay, before I go through this, let me see how many students I have. Okay, I think most of you are in. So, I forgot if I announced this before, but first of all, I think last lesson I mentioned that to have your homework for submission today. Okay, then I like considered it again, and I thought that it's probably a bit too tight for you, because our lesson is actually on Wednesday. So therefore, homework for submission, please submit next Tuesday instead. Okay, next Tuesday. So at least you have over the weekend to to do your homework, and then yeah, I think I did mention this, that I have posted a past year paper that you can find in files, right? And this is just a question paper, so please do it on your own, and then I will post and perhaps also go through some of the tougher questions, right, during our lesson on Wednesday next week. All right, so at least you check your answer. For those who you got wrong and you don't understand what's the approach, then you can ask me next Wednesday. Okay, so just 2 days before your midterm on Friday, on next Friday. So let's continue with this function, which is the reciprocal of x. And we're supposed to use the first principles definition, the limit definition, right, to find the slope. So hence, the slope, let's call that m. So slope m, which is also equivalent to f prime. So by the way, this is known as the slope function, okay? Because we don't sub in any particular value of x, we find the general function first. So we just use the limit definition. So it's always the same. F of x plus h minus f of x over h. Okay, now in fact, this is known as the forward difference definition of the derivative. Okay, forward difference, because it is known as forward difference. Okay, let me just put a note here. This guy, this is known as the forward difference definition. Okay, this is the forward difference definition. And why is that so? Because if you look at your, for example, the graph looks like that, right? I'm just making this up, of course. So let's say this is your f of x, right? And if you want to find what is the f prime at x, so where is your x? Maybe I say that this is my x, okay? So this is my x. So if I want to find the slope or the slope of the tangent here, right? So what I do is that I take the forward difference, which is I take this as the reference point, and then I move forward. Okay, so my secant line, right, is actually going, one point is at x, the other point is at x plus h, right? So therefore, I take the function value, the difference in the function value, divided by the difference in the x value. Okay, so therefore, vertical divided by horizontal, so-called changes, right? I get the gradient. However, there's actually no need to use the forward difference. Okay, you can also use the backward difference. So if you want to use the backward difference, you can, because you can actually just find another point, right, that is behind. Okay, so let me extend this a bit. Okay, this is my f of x. So if you want, right, you can also use backward difference. So backward difference is like that. So you take a point at the back, then this is still that point, and then you draw a secant line. Okay, so you can see this blue line here, right? And if you try to find the slope of this line, it is actually giving me, right, f of x plus, or rather, f of x minus f of x minus h over h. Do you realize that? Okay, so because this is like x minus h, what? This guy is x minus h. So you take f of x at this point, then minus f of x minus h. You can see that, huh? Okay, so still change in f, change in the y value. Then divided by h, because x minus h, right? You still get h for this gradient here. I mean, for this change in x here. So therefore, this guy, right, is known as backward difference. So if you take the limit as h go to 0 using this backward difference, right, you can also derive the slope function, okay, or the gradient function. So this guy, right, is known as backward difference. Okay, but conceptually, both are equivalent. You can see now, conceptually, right, you're just taking the secant line, the slope of the secant line, and then taking the limit as the change in x go to 0. Okay, so it doesn't really matter if you take forward difference or you take backward difference, because you're all converging, right, towards that tangent line, okay, at x. All right, so clearly there's also another combination of the forward difference and the backward difference. And if you take minus h to plus h, right, then actually we have one more called the central difference. Okay, this orange line here, right, you can take f of x plus h minus f of x minus h divide by 2h. Okay, because this is plus h minus h, right? So 2h here. So therefore, that is known as the central difference. Okay, so I mean, just different variations of the same idea. Okay, basically to approximate the tangent slope. Okay, so this one not tested, just for your knowledge. All right, but you can see that the concept is being applied in multiple ways. So coming back to evaluate this guy, right? So we just substitute the function, which is 1 over x. So this guy is really giving me 1 over x plus h. So you can see when this is x plus h, right, you must just replace x by x plus h. Okay, because this is x, right? Whatever the input is, just plug it in. So minus 1 over x, then over h lah. Okay, so of course this looks a bit funky, and you will want to kind of like simplify it by making the common denominator. So hence I just multiply by x over x here. So hence you get x minus x plus h over x times x plus h. Then, oops, then over h. Is that right? Let me just put the limit a bit lower, because it applies to the entire fraction. Okay, so of course in the problem, x plus h over x plus h. Okay, so it's 1, so I don't change this term. And then this guy, right, just multiply by x over x. Can Okay, so by doing that, right, I have common denominator. I just combine them. Then this is x minus x plus h. Okay, so you remember to bracket this term up because there's a minus here. So therefore, you can simplify this guy, which is, so this is x minus x, right? But minus h. So left with minus h over. Then there's a h here, right? Then this h can bring up, okay? Because you divide by this and then you divide by this again. So therefore the h can be combined at the common denominator. So hx, x plus h. Okay? So basically this one just arithmetic manipulation. So hence we observe that there's h here, there's a h here. So clearly we can strike it off or divide it off. So hence I'm only left with minus 1 minus 1 over x plus h. Okay, so when I take h go to 0, then it's just x times x, what? Or x times x plus 0. So hence x times x. So therefore, this is quite clearly minus 1 over x squared. Okay, maybe I just write one more step. And this is really minus 1 over x squared. Okay, so hence, indeed, my slope, f prime, right? F prime x is just minus 1 over x squared. Okay, and you will see that this actually agrees with the differentiation identity, right? That x to the power of n is actually nx n minus 1. Okay, so this is something you probably learn in your secondary school or your poly days. All right, so because this is n equals to minus 1, right? So if you use this, right, you get d dx of x to the power of minus 1. So hence, you can see that n you bring down, so minus 1. Then x, let me put a bracket. Then you have x to the power of minus 1 minus 1. So hence, isn't this minus 1 times x to the power of minus 2? Then this is minus 1 over x squared, what? Okay, so you can see this guy, agree with this guy, right? So this is using the general formula for differentiation. This is, of course, deriving the derivative of 1 over x through first principles. Okay, both must agree. Okay, because that's how the formula comes about in the first place. Questions? Okay, so I hope you're fine with this. And just to finish up the problem, we're supposed to find the slope of the curve at x equals to a. So quite clearly, the curve at slope equal the slope of the curve at x equals to a will be just f of a. So at x equals to a, so the slope is actually given by f prime at x equals to a. So f prime of a, so minus 1 over a squared. Okay, so when we look at this guy, right, actually, you observe that this gradient is always negative. Did you observe that? Because x squared, regardless of what x is, right, x squared is always positive. So 1 over positive, then you have a negative here, right, which means that your gradient is always negative, regardless of where x is, right? It's always negative, except at x equals to 0, it will be undefined, clearly, all right? So we can actually verify that graphically, right? Because if you look at your 1 over x graph, you actually might observe that there's nowhere where the gradient is positive. Okay, so therefore, let's say this is my 1 over x graph. So don't you agree that the gradient is everywhere negative? Look at the tangent lines. Okay, so all negative gradients. Right? So therefore, this minus 1 over x squared looks legit, right? And we can inspect that as your x goes closer and closer to x equals to 0, you realize that the gradient becomes steeper. Okay, so as further away from x equals to 0, your gradient becomes shallower. Okay, so that is in total agreement with this function here, right? As x goes towards 0, this fraction becomes smaller. So 1 over something smaller. Apologies, let me say that again. So as x goes towards 0, this x squared becomes smaller. So 1 over something smaller, right, means you have this thing which is bigger, but this is a negative. So hence it is a larger negative gradient. Okay. So with that, we can easily solve this problem here. So where is the slope equivalent to minus 1/4? Okay, because we know what is our f prime already. So hence we just use it accordingly. So let f prime of x equivalent to minus 1/4. So but f prime of x, right, is actually minus 1 over x squared. So this is minus 1/4. So hence, by inspection, we can see that x squared must be equivalent to 4. Okay, so x is equivalent to plus minus 2. Okay, so you might observe that at plus minus 2, right, you have 2 points of exactly the same slope. Okay, because this function is a odd function, right? It's an odd function. Okay, so therefore you get 2 points, one on the negative side, the other one on the positive side, where you have exactly the same negative gradient. Okay, so questions on this second part? That's good. Move on. We'll talk about normal lines here. So the normal line to the curve is actually just a line that is perpendicular to the tangent line. Okay, and then we actually discussed this before already, right? The slope of the normal is actually minus 1 over the slope of the tangent. Okay, if you just look back at your slides for linear function. Okay, I think we derived this before, showing the two triangles, and then the triangle, one of the triangle is actually rotated 90 degrees. Okay, so I think I can just quickly do a sketch here, and you probably can see the similarity. So what is the slope here? Slope here is given by this pink triangle. Okay, you see the slope here. Then what is the normal triangle? The normal slope, right, is given by this green triangle. You see that? So what is the relationship? The relationship, right, is actually you take this triangle, you rotate 90 degree. Rotate 90 degree. And then you get this green triangle. Okay? So which means to say that the change in x here and the change in y, they reverse. So you can see this change in y, right, after you rotate 90 degree. Okay? Wait, let me see. Okay, it's not actually not rotating 90 degree. Let me see. Okay, let me draw the other way because I want it to rotate 90 degree. So I'm going to draw this way. It's clearer. Okay, that looks good. So therefore, you can see that as you rotate 90 degree, right, the change in y now become here. So this is your change in y. Okay, then the change in x become here, right? So this is the change in x. But then what happened? This change in y over change in x, right? And change in y is positive, right? Because it's going up. Change in y is positive. Change in x is positive also. Now you look at what happens here. So now change in x, right? This is the change in x. This is the old change in x. You see? So this change in x, right, becomes negative because it's going down. Then this change in y is actually the change in x for this green triangle here. So therefore, you have to have a negative here. Okay, because positive slope will become negative slope after you have rotated 90 degrees. Okay, and vice versa, right? So hence you have a minus 1 over. Okay, so therefore, from just by inspection here, right, we can see that. So this is my change in x. in y, then this change is actually equals to change in y. Okay, so I'm talking about the green part here, right? So hence, right, we can see that the slope of the normal line is actually equivalent to change in y over change in x. Okay, change in y over change in x. And in this case, right, in this case, this change in y is negative. Okay, it's actually negative. So therefore, let me just write a change in negative change in y here. Okay, I put change in y as an absolute, right, which means that it is positive. So negative, you see, negative slope. So therefore, right, this guy is actually equivalent to negative, but change in y is the old change in x. What? This change in this change in y is the old change in x. So therefore, this is actually minus change in x over change in y. Okay, so isn't this equivalent to minus 1 over, right? Because this is 1 over change in y over change in x. Okay, so clearly we can write this as minus 1 over, this guy is gradient of the tangent. Okay, so just by looking at triangles and rotating it, right, you can come up with this identity here, or the equation here. So therefore, we're just going to make use of this. Okay, so I mean, put it in another way, right? If I write this in another way, we can have mn, which is the gradient of the normal, multiplied by the gradient of the tangent, is giving us minus 1. Okay, so this is another so-called equation that you can use to find the gradient of one given. So let's use this knowledge here, right? By the way, you can also use dot product between vectors. Okay, if you take this vector dot this vector, right, you're going to get 0. Right? If you, I don't know if you guys have learned vector dot product already. Okay, but if you want, right, you can try using that. Okay, vector dot product between this vector and this vector equivalent to 0, then you will straight away get this equation here. So let's apply that. So we are given this function f of x equals to 4 minus x squared. We are supposed to find the equation for the normal to the curve at x equals to 1. Okay, so right, the steps are here, but it's quite intuitive. Basically, what we do, right, is to find the slope of the tangent first. Okay, so we can find the slope of the tangent first using our limit definition, right? Or clearly, if you're not asked to use the limit definition to find the slope, you can of course just use your differentiation directly. Okay, but at this juncture, maybe let us use our limit definition. And once we get the slope of the tangent, then basically we just use this identity, right, to find the slope of the normal. Okay, so once we get the slope of the normal, we will need a point. So the point is at x equal to 1. So therefore, you have a point, you have the slope. So therefore, you can use the point slope form to get the linear equation. Okay, so let me draw a graph to show you that. All right, so hence the idea is this. Okay, 4 minus x squared. So of course we can draw that guy quite easily. So because this minus x squared plus 4, so I know that the asymptote, not asymptote, the vertex is at 4, or the y-intercept is at 4, and then this is a minus x squared. Okay, so y equals to 4 minus x squared. Then we have x equals to 1. So at x equals to 1, maybe is here. So therefore, you are looking at a normal here. So what we want is actually this line. Okay, that's not very perpendicular. Let me try again. Yeah, that looks a lot. Okay, so this is the normal line. Let's call it n. All right, and then the slope of the tangent line will clearly be just this guy. So this is my tangent line. So okay, maybe I call this mt lah, mt. And this guy, the slope is given by mn. Okay, right? So of course, let's find mt first, right? Let's find mt first. So that's the idea. And MT, which is the slope of tangent, let me just write a definition to be clear. Slope of tangent. So let's call that MT. So MT is actually taking the limit of the secant line. Okay, but the function never changed. So the function is just 4 minus x plus h square minus x square. Sorry, minus 4 minus x square divided by h. Is that okay? I skipped the first step of writing f of x plus h minus f of x. Okay, but you probably can see that here, right? f of x plus h, right? But x plus h, just replace x by x plus h. So you can see x square now become x plus h whole thing square. Oh, by the way, this square should be outside here. Okay, be very careful. So hence, okay. I'm going to do a shortcut, okay? Because I don't want to redo everything again. Since, right, we just now already found out what is the gradient for x squared already, okay? So instead of messing with this, right, why not we make use of the result that we obtained previously, okay? So let me show you what I mean by that, right? So if you look at this guy, right, it's actually comprised of two terms, right? So this is equivalent to the limit. So this is 4 minus 4. So 4 minus 4, a constant. So that is clearly to be 0. Then this becomes minus of x plus h square plus x square over h. And this guy looks awfully familiar. So what I can do, right, is just factorize out minus. Then this will nicely become x plus h square, x plus h square minus x square. See, I factorize all this minus, so therefore this become minus, okay, because minus become plus here, so over h. So far, okay, right? 4 minus 4 just remove, okay, delete them away. So just minus off away. So hence, right, look at this guy. Isn't this guy the same as what we got here? Exactly the same. So hence 2x. So this chunk is 2x minus 2x. Okay, so we know that is correct because for the students who have learned differentiation before, you know that differentiate 4 get 0, differentiate minus x squared get minus 2x. Okay, quite clearly. So therefore, let me just put a note here. This guy from previous example. Okay? Questions? You get minus 2x here? Okay, so I hope this is clear. If not, right, you can expand out and then you will still get the same result. So therefore, at minus 2x here, so now we can gradient of the tangent already. So therefore, at x equals to 1. So hence my MT, right, is actually equivalent to my f of 1 or f prime of 1. Okay, by the way, this is my f prime. So f prime of 1. So hence it's minus 2. Okay, just minus 2 times 1, so minus 2. So therefore, what is the gradient of the normal? So then we can write, therefore, gradient or slope of normal. So mn is equals to 1 over or minus 1 over mt, right? So minus 1 over mt. So this is minus 1 over minus 2. So this is a positive half. Is that right? Okay, positive half. So if you look back at our drawing, I think it should be legit that this mt is a minus 2. Okay, mt is minus 2, essentially downward sloping, right? So minus 2. Then mn is half. So mn, right, is positive sloping and it's half. Okay, of course, my drawing is not perfectly here, right? By right, this MT should be downward sloping more, okay, in the sense that it is steeper gradient downslope. So once we get that, right, then we can just use the point slope form. So using, wait, I need to find what is my y at x equals to 1. Okay, so y is equivalent to f of 1 is 4 minus 1 square. So hence that looks like a 3. Okay, then use point slope form. Point slope form. Then we get y minus y1. Y1 is just 3 equals to mn. Okay, sorry, let me just write one more step. So y minus y1 equals to mn x minus x1. Okay, so this is the point slope form of the equation. So y minus 3 is equivalent to half x minus 1. Okay, so therefore I can write it as y is equivalent to half x. So this looks like a minus half plus 3, right? So therefore it will be plus 5 over 2. Okay, so this is the equation of the normal. Questions? Looks good. So let's move on. Okay, so key concepts and summary, right? Basically, I just leave you to go through yourself, right? So we are done with finding the slopes of tangents and normals. So let's move on to week 5's material, which is the last week of material before our term break. So week 4, material will be fully tested in your midterm exam. So we'll see how much we can cover for this week 5 material, and then we will stop there. Okay, I will make an announcement on the slide number that your midterm will test you until. So now we look at the concept of velocities and rate of change, which is a direct application of the limit definition of the derivative, right, that we have gone through. So let's see. Let me get back my chat box. So if you have learned kinematics, you might have gone through this before, right? What is actually a velocity? So the velocity defined as the rate of change of displacement, okay? Rate of change of displacement. So let me just write a note here. So this guy is defined as rate of change of displacement. Okay, or in short, ds dt. Whenever you see rate, right, unless otherwise specified, rate is always pertaining to time. Okay, so this rate of change, right, is always with respect to time. Okay, unless otherwise specified, of course. So therefore, with respect to time, you see that the denominator here, right, is always dt. Okay, So as you know, we name this as change of displacement divided by change of time. Okay, so therefore this is actually rate of change of displacement with respect to time. Okay, so therefore this ds dt, right, if you look at this diagram here, it demonstrates this idea very well. Because if let's say this s is your displacement function, and take note that displacement has a polarity, meaning to say it has a direction. So if you say going towards the right as positive displacement, that means going towards the left when the position of the object is on the left side of the 0 point, then this is negative displacement. Okay, so this is positive displacement, this is negative displacement. Okay, so hence, if you have this displacement function s, right, which is given by f of t, okay, in short, of course, you can just write s of t directly, right? So hence, after some time t, for example, right, the particle travels from this point to this point, so there's a change in displacement. Okay, there's a change in displacement. So therefore, this change in position, right, or change in displacement is given by the function value at t equals to a plus h minus the function value at t equals to a. Okay, so change in position generally, right, will be given by f of x plus h minus f of x. Okay, of course, x can be any general position x. Okay, it's just that in this example, right? Oops. Oh, sorry, it should be t plus h. Okay, because I use t here. So hence this will be t, and this will be t. So this is at any general time t. Okay, so the f is actually the position, right? And then this t, right, is your input. So this is at any general time t. Okay, need not be t equals to a. So the velocity, as I mentioned, right, is given by ds dt. So, but we previously have learned that ds dt is really just taking the limit, right, of the finite change in your displacement function. So therefore, displacement is just given by this numerator, and then time, right, is just given by this denominator. So average velocity here, right, more concretely, I should write it as change in displacement over change in time. Okay, change in displacement over change in time. This is better, right? So if you look at actually what does this change in displacement over change in time means, you can inspect that this is your f of a plus h and this is your f of a. So quite clearly this numerator is representing the change in the y value. Okay, so therefore this is f of a plus h minus f of a. Okay, change in y value. Then quite clearly, this is just change in time, which is given by the change in the x value. Okay, change in y over change in x. So if you take the limit, then clearly it will give you the ds dt. So therefore, this guy, right, which is also the ds dt. Okay, let me just write it here. ds dt at t equals to a. Okay, because this is v of a here. If your a is t, right, then it would be just the dt. All right, questions? So it's just the same limit concept applied to displacement. Okay, but we don't care whether it's a displacement or what, right? It applies to some continuous function, and we can just apply. Okay, in fact, the condition for the limit of this guy to exist, right, is that the function here must be continuous and smooth. Okay, so we talk about the smooth requirement later on. It cannot have a kink, okay, so it cannot be, you know, an abrupt change in direction, okay, over the curve. So this is what I just mentioned, right? So of course, this ds dt here, right, is also in short given as s prime t. Okay, so s prime t. ds dt is in fact s prime t. So therefore, they use F prime here to represent prime A, right? So in other words, F prime A is the velocity of the particle at t equals to A. Okay? So therefore, if this is the velocity, because velocity involves direction, okay, involves direction. So hence, if the velocity is negative or positive, then we know the direction that the particle is actually going. So as you can see from here, this is a positive velocity, right? So which means that the displacement is increasing. As you can see, displacement over this point, right, before to after, it is actually increasing. So therefore, the gradient, which is the velocity, is positive. Okay, the slope is positive. So therefore, let me write here. So this F prime A is the velocity of the particle. And if the velocity is positive, that means S of t increases. Okay, it's increasing. However, if the velocity is negative, then S of t is decreasing. Okay, so quite clearly, we see that, let's say this is our S of t, and this is t. So hence, if this is increasing, so therefore S of t is increasing, so V is positive. Correspondingly, if S is decreasing, you can see the displacement, right? Decreasing, going back towards the origin, right? So therefore, this is V negative. Okay, so the velocity actually represents the slope of your displacement function. Okay, because that's how it's defined in the first place. So hence, if you understand the concept of velocity in the sense that it is representing the gradient of the displacement function, then you must agree that the speed, right? Usually we say that speed, we don't care about the direction anymore. Okay, so the speed is just the modulus of the velocity function. Okay, so this guy is actually, so speed generally will be the absolute of the velocity function. Okay, so whenever it's negative, right, you just throw away the negative sign and you just write the positive variation. Let's look at this example to apply the concept of velocity. So we have a ball that is dropped from the upper observation deck of some tower 450 meters above the ground. Looks awfully familiar. Okay, I think we have done this before. Okay, so let's draw the representation. So this is our tower, and then we have a ball that is dropped from the top. So this guy is actually 450 meters. You see our ball is here. Okay, and therefore this ball, right, is dropped. So the equation of motion is actually 4.9 t squared. Okay, then I have to ask you a conceptual question. If you look at this function equals to 4.9 t squared, can you tell me where is the reference point? Like for example, from here, right, there is a reference point. The reference point is at t equals to 0. Okay, so this is the origin. Okay, so origin of displacement of S of t, right? This guy. So now, if I look at this example, can someone tell me where is the origin of the displacement if you look at 4.9 t squared? Anyone? At 450 meters. Okay, so conceptually is correct, okay, but you have to be careful when you say at 450 meters, right? So let me answer that. So at 450 meters is correct, okay, and the direction of S, right? So the origin is actually here. Let me use blue. Okay, let me draw this ball a bit because it's treated as a particle. So let me draw it a bit smaller. Okay. And then it is actually at 450 meters, but at 450 meters, S equals to 0. And S of t is pointing down. Okay, why do I say that? Because if you look at this function, it's 4.9 t squared. So as t progresses from 0 onwards, this S function, right, the displacement function is always increasing, right? So hence this must be the origin, okay, not the ground, right? Not the ground. This must be the origin, right? So S equals to 0 here, and then S of t is pointing downwards, and pointing downwards is positive displacement. Is that all right? Okay. Yeah, S of t and F of t is the same, right? Just like I use S of t directly. Okay. So therefore, sometimes you write like y equals to F of t. Sometimes we write y of t directly, or we can also write F of t directly. Okay. So therefore, this is just different ways of writing the same function. All right. So you can see that this S of t is coming down positive and starting from S equals to 0 at the top of the towel. So now we are supposed to find what is the velocity of the ball after 5 seconds. Okay, so after 5 seconds, right, the ball will have dropped and then would have accelerated. So by the way, this 4.9 is actually g divided by 2. Okay, g is 9.81, so it's about 9.8. If you divide by 2, you get 4.9. Right, so we can actually derive this from Newton's second law, F equals to ma. Okay, so we're not going to that. So what is the velocity of the ball after 5 seconds? So first of all, right, we got to find the velocity function first, right? After we get the velocity function, then we just sub in 5, okay? So that's actually no big deal. Then that's for A. So for B, right, what is the average velocity from the time interval, in the time interval t equals to 1 to 5 seconds? So that is practically finding the change in displacement over the change in time from 1 to 5 seconds. Okay, so if you look at it from a perspective, right, this is actually finding the slope of the secant line. So then this should be C. I think there's a typo here. So how fast is the ball traveling when it hits the ground? So which means that you want to know the velocity function or the velocity when this ball is at a displacement of 450 meters. Okay, so conceptually, that's how we tackle these 3 parts here, right? But let me just draw you a graph of the velocity function here, or sorry, of the displacement function here, so that you can understand this better. So this is S of t, this is t, right? So it starts from 0, At t equals to 0, S equals to 0. So it starts dropping. And you can see that it is 4.9 t squared. So clearly, right, it has to be this way. Okay? So 4.9 t squared, right, quadratic function, right? Quadratic function. So therefore, this is S of t equals to 4.9 t squared. Okay? So hence, we are supposed to find the velocity of the ball. So velocity of the ball at 5 seconds. So at 5 seconds, right, is at 5. So you want to know what is the instantaneous slope. Okay? You want to know what is this V of t, right? The instantaneous slope, or rather V at 5. Okay, so let's tackle that. So we have V of t is equivalent to ds dt. Okay, so derivative. So this is actually equivalent to the limit h go to 0. Then you have s of, or rather, okay, I use s directly lah. No need to use f of t. So s of t plus h, right, minus s of t divided by h. Okay, so hence this is really just the same stuff that we have been going through. Okay, so this is 4.9 t plus h square minus 4.9 t square over h. Okay, but clearly this is 4.9, this is 4.9, so we can factorize out the 4.9. Because 4.9 is a constant, so we factorize out of the limit operation, and we got back what we have gone through previously. Okay, so therefore this guy, right, is just 2t. So 4.9, this limit is giving me 2t. All right, so hence we get 9.8t. Okay, so this is my velocity function. My velocity is actually linear, right? Linearly increasing pertaining to time t, and the constant or the coefficient is actually, or the gradient is 9.8. Any questions? Okay, so you must agree that when you differentiate this, right, you bring down the power 2, right? So 2 times 4.9, 9.8, the power 2 minus 1, so you get just e to the power of 1. We should ask to find the gradient velocity, can we use differentiation? Okay, good question. So as I mentioned just now, it depends on the question, right? So if the question say use the fundamental definition of the limit to find the velocity, then you have to do this. Okay, then you have to do this. But if they never state, then you can just use differentiation. Is that all right? So of course, in the midterm, I will have some questions that will explicitly state that you have to use the limit operation. Okay, because this is part of the syllabus that you should be proficient in. Okay, listen. Right, so I will state if you need to use the limit operation. Okay, if I didn't state that, then you can just use differentiation, right? So hence we get 9.8t already. So after we get 9.8t, our objective is to find what is the velocity. So at t equals to 5 seconds, then v of 5 is just 9.8 times 5. Okay, so 9.8 times 5 is what? 98 divided by 2. 98 divided by 2. So that is actually 49, right? No. 9. Yeah, 98 divided by 2 is 49. Okay, so it's actually 49 meters per second. Okay, assuming that did they state? Yeah, it's meters. Okay, so this is meters and t is in seconds, right? 5 seconds here, and then this is meters here. So therefore, the speed is actually meters per second. Okay, and then because you can see that this is change in displacement. So displacement is in meter. So meter minus meter, right? Still meter, change in displacement, meter. Then this is change in time. So change in time. Time is seconds. So therefore, this has to be meters per second. All right. So therefore, next, part B. For part B, right, what is the average velocity for the interval 1 to 5 seconds? So 1 to 5 seconds, we can actually represent this on the graph here. And that is to find the slope of the secant line. So let's say this is my 1 second. This is my 1 second. So you can see that I can join these 2 points, right? Okay. So this guy, right, is actually V average between 1 to 5. Okay, let me just label this as VAVG, right? Average velocity, right, between t equals to 1 to 5. So hence, V. So average velocity in t from 1 to 5 is equivalent to, okay, let me call that V average. So hence, this guy is what? S of 5 minus S of 1 divided by 5 minus 1. Is that all right? Because this is change in S. Okay, wait. Let me write one more step. So the average velocity is actually change in displacement over change of time. Okay? So change of displacement, right, over this change in time. So it must be S at 5 minus the displacement at 1 over 5 minus 1. Okay? So that is in agreement with finding the slope of the secant line here, as you can see, right? S of 5 minus S of 1 divided by 5 minus 1. Okay, the gap. So come back here. So you know that this is 4.9 4.9. So maybe let me factorize that out. So you get 5 squared minus 1 squared. So this is 4.9 times 4. Oops, no, it's 4.9 times 24. Okay, then this is over 4. Then this is over 4. Okay, so of course you can press your calculator. 4.9 times 6 then. 39.4. So by inspection, we can see that this 29.4 looks correct because this is of a shallower gradient as compared to 49. Okay, and that is in agreement with our slopes here. Right, this is 49, then this one must be a shallower gradient, right? So it should be 29.4. Okay. So moving on, the last part. How fast is the ball traveling when it hits the ground? So which means that you want to find the velocity when it hit the ground. Okay, but you don't know what is the time when it hits the ground, right? Okay, but you can find what? Because you know that when it hits the ground, S must be 450. Okay, the displacement must have traveled 450 meters, right? When it hits the ground. Okay, so which means at this stage, S equals to positive 450. Okay, so when it's here, when the ball is here, so therefore, now we come to this part. When ball hits ground, S equals to 450. So hence, T squared equals to 450 divided by 4.9. Then of course we can find out what's T. So it's just the square root of this guy. So it's actually square root of 450 divided by 4.9. So it's 9.583. Okay, I'm just going to use 9.58 then. So T equals to 9.58 seconds. Okay, so of course you reject the negative, right? Reject minus 9.58 seconds. Okay, so once you have that, then you just substitute. So therefore, the velocity when it hits the ground, right, is at t equals to 9.58 seconds. So you can just take 9.8 multiplied by 9.58. So that should give us the answer. $93.9. So this looks like 93.9 meters per second. Okay, so the value should make sense because by the time it hits the ground, right, the velocity would have been accelerated to a much faster value. Okay, so after 9 seconds, after 9.5 seconds, right, you can see that the velocity is indeed much larger. Okay, so as compared to the average velocity here, and then at 5 seconds, it is 49 meters per second. Questions on this example? So if you are good, let's take a break. Hold on. So we have Floyd asking, the question mentioned how fast in part C, so it refers to the speed. Let me see. Yeah, I mean, you can, how fast, right? Yeah, it actually refers to the speed, but the speed is also the velocity in that sense. Okay, since as you can see, given this S function, right, it is always positive. Okay, this S function, 4.9 t squared is always positive, right? So how fast is indeed the speed, right? It's indeed the speed, but the speed is also the velocity. Okay, so good point there. So this velocity, also the speed. Let me just write a note here. Also the speed. Okay. Any other questions? So this is, let's break until 12:20. Okay, let's move on. Okay, let me just write a note here. Now let's talk about the units of the rates of change. So in our example just now, we looked at the velocity or speed. So I mentioned before that the change in displacement is meters and the change in time is seconds. So therefore velocity, right, is change in displacement over change in time. So therefore there is a meters per second. And the intuitive understanding of velocity is how fast, right? So fast is about how much you move in meters per unit second. Okay, so how much you move in meters per unit second. So that's equivalent to saying, right? For example, if you were to have a velocity of 10 meters per second, what does that mean? That means when 1 second traverse, after 1 second, you would have moved by 10 meters. Okay, so that's the idea there. So sometimes, of course, you're familiar with the speed on a vehicle, for example, 100 kilometers per hour. So that actually represents in 1 hour, you would have traversed 100 kilometers. Okay, so 100 kilometers per hour, right? So in 1 hour, you would have moved by 100 kilometers. Okay, so that's the meaning of speed or velocity. Then, of course, we can have also the change of area pertaining to time. So rate of change of area. So in this case, right, area can be, for example, in cm square. So therefore, we can have cm square per second. Okay, rate of change of area. Then we can also have rate of change of balloon. Rate of change of volume, right? For example, in a balloon. Okay, and that is can be described by cm cube per second. Okay, so for example, when you blow a balloon, the balloon increases in its volume. So it is increasing at a certain cm cube per second. Okay, so then of course slope here is just change in y over change in x. So the rate, so sometimes we can say change in y over change in x, right, is also defined as the rate of change of y with respect to x. Okay, with respect to x. But however, when we say rate of change, right, we don't say with respect to what, right? So usually that rate of change is pertaining or with respect to time. So this is something that we have seen before already. So instantaneous rate of change. And this blue line is actually giving us the average rate of change. Okay. So I think you can pretty much go through this yourself. Right. So average rate of change given by the slope of the blue line, instantaneous rate of change given by the slope of the tangent line. Okay, so the tangent line is this pink line here. Right? You can see average rate of change, right, is actually the slope of your secant line. Okay, so instantaneous, you just take the limit, h go to 0, you get that tangent line. All right. So as I mentioned before, this is the f prime. Okay, definition of f prime. So let's take a look at this example demonstrating the rate of change, right? Not pertaining to speed or not pertaining to displacement, but pertaining to something more commonly encountered in our daily life. We have a manufacturer that produces boats of fabric with a fixed width. Okay, so a boat of fabric is just like when you go People's Park Center and they sell a lot of fabric or cloth. Usually have this center row and then maybe your fabric is rolled outside. Okay, so this is actually one boat of fabric. Okay, one boat of fabric. So this is your cloth, of course. So hence, the cost of producing X yards of this fabric is F of X dollars. So C is the cost function. Okay, or generally you can just put it as C of X. Okay, so hence, what is the meaning of f prime x and what are its units? So basically you want, what is the derivative, c prime or f prime? So this cost, right, is dollars. X is yards. Any guesses? What is the meaning of f prime in this case? No guesses? Very good. Okay, very good. Price per yard. So how do we know that? Okay, let's see. So A. So you can see f prime, right? F prime x is basically equivalent to limit h go to 0, f of x plus h, or rather, instead of writing that, I just write change in f over change in x. Okay, but change in f over change in x, what is this? This is change in cost. Change in cost. What is change in cost? Change in cost is dollar. Okay, the unit is dollar. Then what is this change in x? Change in length. So change in length. Okay, because x is yards. Yards is a length. 1 yard is 1 length, right? I mean 1 yard is a length. So therefore, change in cost over change in length. So the length here is actually yard. The unit is yard. Can be meters or whatever, doesn't matter. So therefore, you can see that this is actually change in cost over change in length, right? So f prime will have the unit dollar per yard. Okay, so therefore, f prime is the change in cost of fabric per yard. Okay, so therefore this is actually dollar per yard. Okay, let me write on the next line. Okay, so the units is dollar per yard. Or you can write dollar per yard also okay. Okay, so it's right here. So that's for part A. In practical terms, what does it mean to say f prime 1000 equals to 9? So since you know it is dollar per yard or price per yard, okay, because this guy is dollars, your unit is dollars, right? So therefore, what does it mean to say f prime 1000 equals to 9? That means, is there like a sentence? Let's say if you were to tell your customer, what would you say? Because you can't say f prime 1000 equals to 9, right? Okay, unless he is unless the customer learned mathematics before, or else he wouldn't understand. So you see, x is what? X is yard, right? So this is the 1000th yard. This guy. 1000 yard. Okay? Any guesses? Then this 9 is what? $9. 1000 yard is $9. Wrong. That's a bit too cheap. Okay? That's a bit too cheap. 1000 yards is $9. Yeah. Okay, the manufacturer will go bankrupt. So if it's f of 1000, not f prime of 1000, then what Kevin say is correct. Okay, if it's f of 1000 equals to 9, then he is correct to say that the cost of 1000 yards is $9. But this is f prime, it's not f. Okay, so therefore, what does this mean? It means to manufacture the 1000 yard it will cause an incremental, okay, let me just continue here, an incremental $9. Is that right? Okay. So therefore, right, this really means for the 1,000 yard, so if you want to produce that additional 1,000 yard, right, you will need to spend an additional $9. Okay, right? Yes, you can say that. Okay, because we say F prime 1,000, right? It's actually an instantaneous change. So therefore, one perspective is that you can view it as, right, if you want to manufacture from the 1,000 to the 1,001 yard, it is approximately $9. Okay, of course, I'm using approximately here because this F prime is actually instantaneous change. Okay, so when we say the 1,000 yard, so which means 1,000 to 1,001, right? It's actually, we are taking an average already, right? So therefore, it's approximately $9 to make 1,000 to 1,000 to 1,001, or as what Kevin said, you can say 999 to 1,000 is also conceptually correct. Okay, so therefore, which do you think is greater, F prime 50, F prime 500, or F prime 5,000? So let me draw a graph to illustrate the concept of this part B further. So let's say this is your cost function, f of x. Okay, cost function. And then this is your yard. So this is x. So hence, okay, let's assume that there is this economy of scale. Okay, there's an economy of scale. So therefore, by right, the cost wouldn't be a linear line. Okay, it should not be a linear line because as you manufacture more and more, right, by right, you should have economy of scale. So therefore, the later yards that you manufacture, right, will be cheaper. Okay, it will get cheaper and cheaper. So therefore, let's consider that you have some, what do you call that? Some initial costs. Okay, so like utilities, manpower, whatever lah, right? So some capital costs, right, that you cannot so-called negate away. So even if you make 0 yards, you still need to pay for those overheads. So by right, this maybe something like that. Okay, so maybe it will flatten off, right, after some time. So you can see at this 1,000 yard, right? So maybe this is 1,000 yard. Okay, at this 1,000 yard, this is your slope. Okay, let me just draw it a bit more nicely. So this tangent slope, the gradient, right, is actually 9. Okay, so this is f of x, right? So this guy, the slope of this tangent line, f prime at 1,000 is actually 9. Okay, it's actually $9. So this is the meaning, right, of saying f prime 1,000 equals to $9. So which means if you are at the 1,000 yard already, you want to make an incremental yard, right? You will need to spend $9. Is that all right? Okay, understand, huh? So therefore, if you understand that, you can actually answer part C intuitively. Which do you think is greater, f prime 50, f prime 500, or f prime 5,000? So if you consider economy of scale, so we consider the economy of scale, right? Wrong spelling. So then by right, we should have f prime 50 is more than f prime 500 is more than f prime 5,000. Okay, so as you can see from here, f prime 50, right, will probably be a lot more expensive. And then F prime 5,000 would definitely be a lot less expensive. Okay, is that all right? Any questions on the concept here of how the derivative is actually presented in a practical problem instead of just being like a number or a function? Oh, can we ask how did I derive this graph? So it's well, I kind of made it up because I understand from the economy of scale, right? Such that, right, my cost function, okay? So you can think of it like you set up a shop, then you want to manufacture some stuff, okay? Then of course, when you set up shop, right, you must engage your workers and then you pay utility. So therefore, even if you manufacture 0 yards, okay, you're still going to pay a certain amount of cost. Okay, you're still going to pay a certain amount of cost because you have overheads and all that. So therefore, we can expect that the cost is going to increase, but it wouldn't logically increase linearly. Because if it increases linearly, right, it will represent that every one additional yard you make, the cost is going to increase by the same amount. Okay, so every additional yard you make, right, you're going to have an incremental cost by the same amount. Okay, so that's not quite correct because usually there is this economy of scale, right? You sell more or you manufacture more, right? Your cost per unit is actually smaller. Okay, so it's like, for example, you sell maybe like 10 cars as compared to when you sell 1,000 cars. Okay, because there's a lot of things that you need to do, right? Whether you sell 10 cars or you sell 1,000 cars. So therefore, when you sell more cars, right, you are going to have a better economy of scale. Okay, so it's like a shop space, like you rent a shop space, right? Because the same shop space, you can sell 10 cars, you can also use it to sell 1,000 cars. So therefore, if you consider that, right, the rental is the same. So therefore, if you split the rental over 1,000 cars, right, you're going to have a smaller cost per car. Okay, so that's economy of scale. Ping Hui asked supply demand theory. This one nothing to do with supply demand. Okay, it's not supply demand. So, so therefore, you can see here, right? This cost is going to get flatter and flatter. Logically, it will not be a horizontal line. Okay, logically, it cannot be a horizontal line, right? It just get flatter and flatter. That's all. Okay, for example, like a logarithmic curve. So you can see that if you try to manufacture a lot, let's say 5,000 down here already. So every 1 yard that you make, right? Because since you already can make 5,000 yard. So if you were to make the 5,001 yard, then the cost wouldn't be a lot already. You understand? Okay. So if you don't know this economy of scale, you can't answer the question. Well, you can assume. You can assume. Okay. So because this one, what do you think is greater, right? So of course, if you feel that there is no economy of scale or you don't know about the economy of scale, then you can say that the cost per yard is constant. Okay, because I mean, from another intuitive perspective, right? You manufacture 1 yard, the cost is the same. Okay, because maybe the raw materials is exactly the same. So if raw materials exactly the same, right, and then you don't have this economy of scale, right? Then you can say that, oh, you make 1 yard always $9. Okay, so if you make 1 yard is always $9, then this function of x, right, is just a linear function. Okay, it's just a linear function. Is that right? Okay. Yeah, so maybe you can go back and think about this, right? This is I don't know, like maybe will be covered in economics subject or something. Okay? Or you can just use your like daily experiences to understand that. Okay. Of course, that is also the reason why Google and Apple and Facebook, as well as all the big companies, got that big. Okay. Because, like, for example, if you buy things from NTUC, like supermarket NTUC, right, it's usually always cheaper than if you were to buy from some shop, maybe in the heartlands. Okay, because NTUC got economy of scale. So when they order, right, they can order a lot. So when they order a lot, right, the seller must provide them with a cheaper price, okay, because they want their business. So they sell by volume, okay. So hence, if you buy from the one small shop, right, because they don't have economy of scale, they don't order so much goods. So therefore, when they buy, right, it's actually so-called more costly for them. Okay, it's just like when you buy from Taobao, right? You sort by the, what do you call that? The number of sales, right? And usually those are the top sellers. Okay, because they got economy of scale, right? So they can, you know, compete against price, right? So they can compete with price, okay, against other manufacturers, right? So economy of scale is important. You want to operate on the right side of this graph here, okay? So that your incremental cost per manufactured item is actually less. Okay, so key concepts, this one I can leave you to go through. Derivatives, so actually we have done this part already. It's just different ways of saying the same thing. So f prime is actually equals to this limit, and f prime is also dy dx, is also df dx lah. Okay, so all these mean the same thing. Y prime dy dx or d dx of f of x, right? They all mean the same thing. Okay, personally, as I mentioned, my favorite is y prime or f prime. Okay, so this is the like nicest to write. I don't like to write like d something like a lot to write. Okay, so this big D and this d over dx, right? They are called differential operators or differentiation operators. Okay, and then this big D, right? Of course, at this juncture, this big D is the same as this d dx, right? It's just different ways of writing. Y prime, f prime, dy dx, df dx, d dx, f of x. They all mean the same thing. This big D here, representing the total differential, right? Actually, this guy in multivariable calculus has a different meaning. Okay, but since we are doing single variable calculus here, so therefore this big D, you just treat it as d dx. Okay, so don't worry about this too much. Personally, I just write y prime or f prime. Okay, most of the time, as you will see. So then when you see like dy dx with a vertical stroke, then they put x equals to a. So really, this is actually equivalent to y prime of a. Y prime of a. So this is actually the same thing. Okay. So y prime of x is dy dx. After you get your dy dx function, right, you can always find the gradient at any particular x by just substituting that x value. So isn't this y prime of a or f prime of a, right? So therefore you can write like this or you can write like this. Okay. So personally, I'll write this way. Okay, using the prime notation. So this notation, I have almost never seen it before. So don't worry about it. Okay, so these are just, all the different ways of pronunciation of this gradient function. Okay, so I leave you to go through this yourself. It's not that important. Of course, in this case, right, this dx does not mean d times x. This d here is actually representing small change. Okay, so this d here, right, d represents small change. Okay, so small change in y over small change in x, right? That's what the derivative or the differentiation of y with respect to x means. Okay, it just means small change. So when you say how small is small, right? Well, it's infinitesimally small, infinitely small. Okay, so h go to 0. Okay, so using the limit concept. Derivative, so this one just basically rewriting what we have learned previously, right? So I'm not going to go through in detail. You can go through yourself. It's just repetitive. So let's look at the derivative of the function of this quadratic expression, x squared minus 8x plus 9 at the number a. Okay, so we're just going to use our limit operation, right? Since this chapter is about using limits. Okay, so I'm just going to do this from scratch. So hence we have f prime x is equivalent to, so limit h go to 0. So it's just going to have f of x plus h minus f of x over h. And this guy is limit h go to 0. Now, this thing, right? Of course, you can take this whole chunk, substitute inside. Okay, but alternatively, right, you can actually take the limit and apply to each of the terms. Okay, I repeat that again. You can take this limit operation, right, and apply to each of the terms as well. Okay, so either way we'll do it, but let me show you the usual way first. So hence, this is really giving me x plus h square minus 8x plus h plus 9. So this is my f of x plus h. Then minus, so at this juncture it's good that you have the big bracket. Then minus f of x, but f of x is just this entire chunk. Okay, so this is my f of x. And then divide by h. Okay, so if you observe, you can actually group the terms together. So limit h go to 0. So look at this x plus h square minus x square. So you can have x plus h square minus x square. That's your first term. Okay, let me box this up. Then we have 8. So this is minus 8 of x plus h plus 8x. So this term and this term, minus minus, so plus. Okay, plus. Let me box this up. Then plus 9 minus 9. Okay, so therefore this whole thing divided by h. Right, so you can see clearly, distinctively 3 terms. Okay, 3 terms. So you might observe that this term is actually the gradient of this term. Observe that. Then this term is the gradient of the second term. Then last term, which is the gradient of this constant term. So the gradient of a constant is 0. Okay, the gradient of a constant is 0, and we know that, right? This is a constant. So what's the gradient of the tangent? 0. Okay, 0 gradient. So hence, we can apply this limit operation to each of the terms here. Okay, so hence, obviously, this first term is going to give us 2x. Second term is going to give us 8. Then the last term is going to give us 0. Okay, so therefore it is just this, right? So 2x minus 8. So let me just write one more step for clarity here. Okay, so this guy is, okay, let me just write one more step. You can, of course, just expand everything out and do it correctly. Oops, did I make a mistake here? Sorry, this should be minus. Okay, because minus is plus. Then I factorize out the minus. So this guy must be a minus. Okay, minus is a plus. Okay, minus. So I just now made a mistake here. So limit. So this guy is the second term. Okay, I just split this entire fraction into 3 small fractions. Okay, then this guy is clearly 0. So hence, this is something that we have done previously. So this is giving me 2x. Okay, then this is also something that we have not done yet. We have not done before yet, but you can see that this guy, right, is actually 8x minus 8x, right? So what you are left? You are left with 8h over h. Okay, because this 8x, right, will minus away this 8x. Let's try that off. Okay, so you're left with 8h over h. Is that right? So once you're left with 8h over h, right, you can divide the h away. So you're left with 8. But what's the limit of a constant? 8. 8. Is that right? So indeed, if you use differentiation directly, 2x minus 8. Okay? So therefore, we can solve the problem. At the number a, clearly it's just f prime of a. Then just do a minus 8 lah. Questions on this example? Okay, if you don't like to break it up into the individual limit terms, right, you can just expand. Okay, you expand this and you expand this and then you just cancel off terms and then take your limit, simplify your expression, take your limit, you still get 2x minus 8. Okay? So derivative here, so it's just repeating what we have gone through. Okay? For point slope formula. So this is something that we have done just now, but for the normal line, okay, but this is the equation of a line, right, tangent to the curve, okay, tangent to the curve. So therefore, let's say we have a curve that looks maybe like that, right, and then we are supposed to find maybe say a tangent here, okay. So let's say we want to know what is the equation of this tangent line, right, this equation of the tangent line, right. So therefore, we will need the f prime. So where is this point? This point is the point A. Let's say this is my axis. So this point is the specified point A. Okay. So if this point is A, then what is this point on the line or on the curve? F of A. Right. So this coordinate is A, F of A, right? Simply because this line is the function f of x. Okay. So therefore, the green line here is the tangent line. And this tangent line, right, the gradient is given by f prime A. So gradient m of tangent is equivalent to f prime A, right, at this point. Okay, you can see this is at point x equals to A. So you can basically see that y minus y1, right, because this coordinate at this point, this coordinate is A, f of A. Okay, so this is my x, x1. This is my y1. Okay, so previously we learned y minus y1 equals to m x minus x1. Okay, so this is the point slope form of the line. Is that right? Okay. It's just that y1, right, is given by a function of a. x1 is just at a, right? You use the given point as a so-called sample point. Then f prime a is just your gradient m. Okay, in this case, this m is given by the gradient, the tangent, right? So just now we applied this to the gradient of the normal. So therefore, we use m sub n there, okay, which is the gradient of the normal. So you can easily find the equation of the tangent line or the normal line using this point slope form. Okay, all it matters is finding a sample point as the proper gradient. Questions? Okay, looks good. Let me see. Okay, so let me just squeeze in a bit and finish up. Let me see. I'm left with 4 minutes. Okay, I tell you what. I'm not going to rush you. Instead, I will work out these two examples offline, and then we will have the midterm exam test until this slide. Okay, so okay, so everything from day one until this point will be tested for your midterm exam. Okay, so I will make an announcement in MS Teams, right? So I'm going to work this out offline and then post it. Okay, post it in MS Teams as well, in under the files, right? So that you can prepare your revision for this guy. Okay, questions? So next Wednesday, we will still have our usual lesson. I will probably go through the past year paper that I posted. Please go and try first, because I do and you understand is totally different from you do yourself. Yes, there is a full worked out answer. So I will post the answer on, I think maybe next Tuesday. So next Tuesday, I post the answer. You look through the workings. So anything you don't understand about the workings or you disagree with the answer, you can check with me on Wednesday during lesson. Okay. Right. So let me just repeat. As I mentioned just now, I will allow you on next Friday during your midterm exam to bring your laptop or your tablet, okay, as well as you can prepare a spreadsheet or a program to assist you in whatever calculations that you need. All right, so which means that I'm definitely going to test you on bisection. So therefore, please get ready your code for bisection, right, or your spreadsheet for bisection, and then you can use those to assist you. Okay, so the main point, of course, as I mentioned, is to integrate your knowledge in mathematics and computing, right, so that you are proficient in it. Okay, in fact, mathematics is always integrated with computing. All right, so you have no questions. That's all for today. Thank you. Goodbye.